the Gaussian integers. The set of Gaussian integers consists of all complex numbers a plus bi, where a and b are integers. The set of Gaussian integers is commonly denoted by the notation integer symbol, brackets, I in between. But it is pronounced Gaussian integers, the set of Gaussian integers. Formally, the set of Gaussian integers equals the set that contains all elements of the form a plus bi such that a, b are in the set of integers. Examples. Determine whether the number or numbers described are in the set of Gaussian integers. Number 1, all x satisfying x squared minus 6x plus 13 equals 0. Number 2, all x satisfying 4x squared minus 8x plus 5 equals 0. Number 3, all x satisfying x cubed plus 1 equals 0. 4, all x and y satisfying 4x squared plus y squared plus 25 equals to 0. Let's take a look at number 1. So we're looking for solutions to our equation x squared minus 6x plus 13 equals 0. X squared minus 6x plus 13 equals 0. We can use the quadratic formula here. X equals the opposite of b, which is the negative of negative 6, which is 6, plus or minus the square root of b squared, in this case negative 6 squared, which is 36, minus 4 times a times c. A in this case is 1, c is 13. So it's minus 4 times 13, which is 52. All over 2 times a. In other words, 2 times 1. 36 minus 52 is negative 16. So you get 6 plus or minus the square root of negative 16 all over 2. But that equals to 6 plus or minus 4i, because the square root of negative 16 is 4i, all over 2. This simplifies into 3 plus or minus 2i. So both of these answers are in fact Gaussian integers. Number 2. All x satisfying 4x squared minus 8x plus 5 equals to 0. Same method of solution. We use the quadratic formula to solve the equation. So you get x equals to negative of negative 8, which is 8, plus or minus the square root of negative 8 squared, which is 64, minus 4 times 4 times 5. 4 times 4 is 16. 16 times 5 is 80. All over 2 times 4, which is 8. This equals to 8 plus or minus the square root of negative 16 all over 8. The square root of negative 16 is 4i. So we end up with 8 plus or minus 4i all over 8. This becomes 8 over 8 plus or minus 4i over 8. In other words, 1 plus or minus a half I. Neither of these solutions are Gaussian integers. the third one, all x satisfying x to the third plus 1 equals to 0. Now let's observe that x cubed plus 1 is the sum of cubes. X cubed plus 1 is x to the third plus 1 to the third. So we can use the sum of cubes formula. So you get x plus 1 times x squared minus x plus 1. So a plus b, a squared minus a times b, in this case x times 1, which is x, plus b squared, which is 1. So if you have x cubed plus 1 equals 0, as is our equation, then that is the same as saying x plus 1 times x squared minus x plus 1 equals 0. One of our solutions is -1. Our remaining solutions come from x squared minus x plus 1 equals 0. Using the quadratic formula, x equals negative of -1, which is 1, plus or minus the square root of -1 squared is 1, minus 4 times 1, which is 4, over 2 times 1, which is 2. So that's 1 plus or minus the square root of -3 over 2, which is the same as 1/2 plus or minus I root of 3 over 2, which are not Gaussian integers. So to answer our question, are all x satisfying this equation Gaussian integers? The answer is no, because some of the solutions were not Gaussian integers. Do note that one of the solutions does happen to be Gaussian integer, but as a whole, the answer is negative. Our last one is 4x squared plus y squared, 4x squared plus y squared plus 25 equals 0. This is the same as, this equation is the same as 2x to the second plus y to the second equals -25. This equation looks familiar to the equation. It looks similar. It's not the same. It looks similar to an equation that has the form a squared plus b squared equals 25. We know that such an equation does happen to have integral solutions. You could have 3 for a, 4 for b, so 3 squared plus 4 squared equals 25. You could have -3, 4, or you could have -3, -4, or you could have 3, -4. So there is a number of solutions to our equation a squared plus b squared equals -25. The only difference between our given equation and the one that we are using as a bridge here is that we're not getting 25, we're getting -25. So in order to achieve the effect of the sum of a square and another square being -25 forces each of these bases to be imaginary numbers. So let's think of all possible combinations. 2x equals, it will have to be 4i or, excuse me, 2i, not 4i. It will have to be 2i, or it would have to be -2i. At the same time, y would have to be -3i or -3i. let me revisit this one, excuse me. So you have 4 squared, sorry. This will have to be 4i. I take it back. Okay, so under those conditions, what do we get? X equals 2i, or x equals negative 2i. X equals 2i, or x equals negative 2i. That's when you divide both sides by 2. And y equals to 3i, or negative 3i. So we conclude that all possible values of x are Gaussian integers and all possible values of y are Gaussian integers. Okay, next, a definition. Let this structure R plus dot be a commutative ring with additive identity 0 and multiplicative identity 1 different than 0. The structure R with addition multiplication is an integral domain if and only if for every elements a, b in R excluding 0, their product is different than 0. So you would need a commutative ring with multiplicative identity different than the additive identity, with the property that when you take any 2 non-zero elements within the ring, their product is different than 0. So that makes that structure an integral domain. Examples. The structure consisting of the integers together with addition and multiplication of integers is an integral domain because the structure of integers, addition, and multiplication happens to be a commutative ring. It has identity, multiplicative identity 1, which is different from the additive identity of 0. And whenever you take the product of any 2 non-zero integers, the result is different than 0. Now, for number 2, let n be greater than 1. Let n greater than 1 be an integer, but not prime. Now, while it is true that the structure consisting of integers modulo n together with addition and multiplication modulo n is a commutative ring with additive identity 0 and multiplicative identity 1 different than 0, the structure fails to be an integral domain. The reason that is the case is because it is possible to take 2 elements within the set of integers modulo n whose product is 0. So to see this, suppose that n is the product a times b in z multiplication, where neither a nor b is 1. And neither a nor b is 0. So a is not equal to 1, 0. B is not equal to 1, 0. So suppose you take the product of those 2. So because since we have n is a times b, then when you reduce modulo n, the remainder is 0. So you get a times b is 0 modulo n. So we have two elements different than 2 elements of Zn. There's 2 elements of Zn, neither of which is 0. But when you take their product, you get the answer 0. This means that the structure Zn under addition and multiplication modulo n is not an integral domain. Definition. Let a and b be Gaussian integers. we say that B divides A, or that B is a divisor of A, in the structure of Gaussian integers if and only if there exists a Gaussian integer z such that A is B times C. This is similar to the divisibility of the integers. A is said to be irreducible or prime in the structure of Gaussian integers if and only if the only divisors of A in the structure of Gaussian integers are plus or minus 1, plus or minus I, plus or minus A, plus or minus IA. But A is neither plus or minus 1, plus or minus I. Examples. 3 plus I divides 9 minus 7i in the structure of Gaussian integers. That is because if I multiply 3 plus I, a Gaussian integer, times 2 minus 3i, which is another Gaussian integer, the result is 9 minus 7i. So 9 minus 7i is the product of two Gaussian integers, neither of which is 9 minus 7i itself, or it's negative, or 9 minus I itself times I, or negative I times 9 minus 7i. Neither of this is 1. Okay. The integer 3 is prime in the structure of Gaussian integers because 3, if you were to write it as a product of two complex numbers, a plus bi, a minus bi, you will get that 3 is a squared plus b squared. But there is no integer solutions that satisfy. There are no integer solutions of this equation. There are no integers a, b which satisfy this equation. You can try and check. So if a were 0, then b squared would be 3, in which case b would be the square root of 3, which is not an integer. If a were 1, then b squared would be 2, which means b would have to be the square root of 2, which is not an integer. However, the integer 2 is not prime in the structure of Gaussian integers. That is because 2 is the product of 1 plus I, 1 minus I, each of which is a prime Gaussian integer. Neither of them is 1, negative 1, I, negative I, and neither of these factors is 2, negative 2, 2i, negative 2i. Okay. Now a theorem. The structure consisting of the Gaussian integers together with addition and multiplication is an integral domain. In order for us to prove this theorem, we need to verify the following 5 items. First, we would need to verify that the structure, Gaussian integers together with addition, is an abelian group. The Gaussian integers together with multiplication is associative. Multiplication distributes over addition in the structure of Gaussian integers. From the left suffices because of the following step, which is the Gaussian integers together with multiplication is commutative, with identity 1 different than 0. So the Gaussian integers under multiplication being commutative allows you to check the distribution from the right and from the left by just doing either one of them. but just verifying either one of them. Step 5. The characteristic property of integral domains is that when you have two elements in the set of Gaussian integers except 0, their product would have to be different than 0. We're going to verify properties 2, 3, and 5. The other two will be left as exercises. Let's try number 5, property number 5. So let's suppose that we have two Gaussian integers a and b. Let's show that their product has to be different than 0. So let's begin. So let a be the Gaussian integers. So suppose, so specifically, let a, so then a equals to alpha 1 plus I beta 1 for some alpha 1 beta 1 in the set of integers. Beta, b equals to alpha 2 plus I beta 2 for some alpha 2 beta 2 in the set of integers. Now, we have to exclude the possibility of either one being 0. So let's say that in this composition, alpha 1 or beta 1 is not equal to 0. Alpha 1 is not equal to 0, or beta 1 is not equal to 0. Alpha 2 is not equal to 0. Beta 2 is not equal to 0. Now suppose that if the product AB were actually equal to 0. Then immediately the conjugate of A times B would have to be 0 as well. In other words, the conjugate of A times the conjugate of B would have to be 0. So if we assume that A times B is 0, it follows that the conjugate of A times the conjugate of B is also 0. So let's do this. Let's multiply left-hand side with left-hand side equals right-hand side times right-hand side. So we're multiplying AB times A conjugate B conjugate. That's equal to 0 times 0, which is still 0. Now let's make the observation that A, so we can commute here, because multiplication of complex numbers is commutative. Once you establish step 4, then you are able to commute this complex multiplication. You're able to commute complex numbers under multiplication. So you get A times A conjugate times B conjugate. Now if you focus on A times the conjugate, so A times the conjugate of A, you will get the following result. Alpha 1 plus I beta 1 multiplied by alpha 1 minus beta 1 I. Remember that the conjugate of a complex numbers is just changing the operation. So here the operation was addition, the conjugate will be subtraction. Observe that that is simply alpha 1 squared plus beta 1 squared. So I find A times the conjugate of A to be alpha 1 squared plus beta 1 squared. In similar fashion, b times the conjugate of b will be alpha 2 squared plus beta 2 squared. Now, this product is equal to 0. These are real numbers. So, in particular, they are integers. So, we know that when you have a product of two integers and it equals 0, then at least one of the two integers must be 0. So, without loss of generality, let's say that it is alpha 1 squared plus beta 1 squared that is 0. What does this imply? If you're squaring an integer and another integer and you're adding the results and get 0, that forces each of the integers to be exactly 0. The contradiction has been reached. Contradiction to what? To the assumption that they cannot both be 0. Alpha 1 is not equal to 0 or beta 1 is not equal to 0. This means that both of them cannot be 0. This conclusion has contradicted that. So, in conclusion, our assumption cannot hold. Therefore, a times b must be different than 0. So, therefore, a b must be different than 0. Okay. Let's verify a multiplication of a Gaussian integers being associative. A good way of doing that is to take 3 Gaussian integers and write them in polar form. So let z1, z2, z3 be, you could use the complex number argument. So let me use complex numbers here. So let z1, z2, z3 be complex numbers. Let's write them in polar form. So zk equals to rk e to the theta ki for some rk greater equals 0, comma, theta k real. So when you multiply z1 times z2 times z3, you get this product right here is going to be by rule of multiplication r1, r2, by rule of multiplication of complex numbers in polar form will be r1, r2, e to the theta 1 plus theta 2 I, and then times r3 e to the theta 3i. Now, by rule of multiplication of complex numbers in polar form, I get that the product of these two complex numbers is r1, r2 times r3 e to the theta 1 plus theta 2 plus theta 3 I. Observe that r1, r2 multiplied times r3 is a multiplication in the set of real numbers. Now we know that multiplication of real numbers is associative, so we can write this as r1 times r2, r3 e to the power. Now, inside these brackets, we have addition of real numbers. We know addition of real numbers is associative, so we can rewrite what's inside the parentheses as inside the brackets as theta 1 plus theta 2 plus theta 3. But what is this equal to now? This is now the product of the complex number in polar form r1 e to the theta 1I times the complex number r2, r3 e to the theta 2 plus theta 3I. What is that? Well, that's z1, and this is the product z2, z3. So we have established that the multiplication of complex numbers is associative. As a consequence, the multiplication of Gaussian integers is associative. Okay, another one that we are going to verify here, this one is going to be through a printout, is that the multiplication distributes over addition in the structure of Gaussian integers. Here we're going to show it for complex numbers in general. So in general, multiplication of complex numbers distributes over addition from the left and from the right. We're verifying one case, the one from the left. You could verify the case from the right as an exercise, but since we have complex numbers under multiplication are commutative, it actually suffices to consider this case only. So we are taking z1 to be a1 plus ib1, z2 to be equal a2 plus ib2, z3 to be equal to a3 plus ib3. So in performing the product z1 times z2 plus z3, we have to use our definition of addition to put c2 plus c3 together. So we did that right here. z2 plus z3 is the real part a2 plus a3 plus the imaginary part b2 plus b3i. And now we're going to proceed to multiply z1, which is a1 plus ib1, times the complex number we just obtained in the parentheses. The rule is you multiply a1 times a2 plus a3 minus b1 times b2 plus b3. That's the real part of the result of their product. And then the imaginary part is is a1 multiplied by b2 plus b3 plus b1 times a2 plus a3. Now, distributing each of the multiplications over additions, so a1, a2 plus a1, a3, and also, so minus b1, b2 minus b1, b3. Similarly, in the parentheses, you get a1, b2 plus a1, b3 plus b1, b2 plus b1, a3. Now, performing the other calculation, which is that of z1, z2 plus z1, z3. So z1 is simply a1 plus ib1, z2 is a2 plus ib2 plus, and then z1, a1 plus ib1, and then z3, a3 plus ib3. When you perform each of those multiplications by using the rule for multiplying complex numbers, you get the highlighted results. So this is supposed to match z1, z2, and then z1, z3. Okay, what's left is the following. Now you have a complex number plus another complex number. So the rule is you add the real parts. So there's the real parts, plus the imaginary parts, you add them up, times I. Notice that that result is the same as the result for the result for Z1, Z2 plus Z1, Z3 is the same as the result for Z1 times the quantity Z2 plus Z3. So you get A1, A2 plus A1, A3 minus B1, B2 minus B1, B3 plus I times A1, B2 plus A1, B3 plus B1, A2 plus B1, A3. Therefore, those two are equal. Okay. To finalize this presentation, let's make a remark. Starts with the fundamental theorem of arithmetic. Every integer greater than 1 has a unique prime factorization, disregarding order. As a consequence of the fundamental theorem of arithmetic, every integer n has a unique representation as a product of primes if n is greater than 1, as a product of primes times -1 if n is less than 1. So here is a question. Since 2 is not prime in this set of Gaussian integers, does this represent a contradiction to the fundamental theorem of arithmetic? Now, remember, 2 is a prime integer, but it's not a prime in the set of Gaussian integers. Now, we have two answers. One answer is no, because the fundamental theorem of arithmetic refers to factorability in Z, not in Zi, the set of Gaussian integers. So if you told me 2 is a prime in the set of integers. So you are not concerned about whether it's not prime outside that set. Now, even if we were to question whether the fundamental theorem of arithmetic holds in the structure of Gaussian integers, the non-primality of 2 does not represent a contradiction, as 2, in fact, has a unique prime factorization in the set of Gaussian integers. Namely, 2 is I multiplied by 1 minus I squared, the prime here being 1 minus I. Okay, so this is the end of our presentation.